Most people start their journey in software as programmers. You learn syntax, you learn loops, you learn data structures, you learn how to make something work. And that's good. Programming is a skill, but engineering is a discipline. And if you stop at programming, you'll always think locally. If you learn engineering, you'll start thinking systemically. Today, we're going to talk about the difference. Not in titles, not in job descriptions, but in mindset. Because the shift from programmer to engineer changes how you approach every problem, and it's one of the most important transitions you can make in your career. The programmer mindset. When you're learning to code, your world is small. You focus on getting the function to return the correct value, fixing syntax errors, passing the unit test, making the algorithm faster, refactoring messy logic. Your feedback loop is immediate. The code compiles or it doesn't. The test passes or it fails. This is important, but it's local. Programming asks, does this piece of code work? And often the answer is binary, yes or no. But real software systems are not binary. They are complex, interconnected, evolving systems. And that's where engineering begins. The engineer mindset. Engineering asks different questions. Not, does this function work? But, where should this responsibility live? What happens when this fails? How will this change in 6 months? Who owns this behavior? How does this affect the rest of the system? What trade-offs are we making? Programming is about correctness in isolation. Engineering is about correctness in context. That context includes other developers, deadlines, users, infrastructure, maintenance, scale, organizational constraints. Software engineering is a socio-technical discipline. It lives at the intersection of people and systems. And that's the shift. 1. Programmers solve tasks. Engineers solve problems. A programmer receives a ticket. Add export functionality. They implement CSV export. The button works. The file downloads. The ticket is closed. From a programming perspective, that's success. An engineer approaches the same request differently. Before touching the code, they ask, who is asking for export and why? Is this for occasional manual use or automated processing? How large can the dataset become? Do we need pagination or streaming? What are the security implications? Should exports be rate limited? Do we need audit logging? What happens if the export fails halfway through? The engineer zooms out from the implementation and looks at the context. Because most software failures don't happen in code. They happen in misunderstanding. If the real need was finance needs monthly reports formatted for accounting software, then a simple CSV button might be the wrong solution entirely. Maybe the real solution is a scheduled report, an automated integration, a dedicated reporting endpoint, or even a data warehouse export pipeline. Engineers don't just complete tasks. They validate that the task actually solves the right problem. Sometimes, the most engineering-oriented response to a ticket is not, I'll build that, but let's clarify what outcome we're aiming for. That shift alone can save weeks of rework. 2. Programmers focus on code. Engineers focus on systems. Programmers think in units. This class, this function, this module, this endpoint. Engineers think in systems, this service, this domain, this workflow, this deployment pipeline, this integration boundary. A programmer might optimize a function to be 20% faster. An engineer asks, does performance here actually matter? Is this the bottleneck? Or are we optimizing the wrong layer? A programmer writes a clean abstraction. An engineer asks, is this abstraction leaking? Will this create coupling? Are we introducing hidden dependencies? Systems have properties that individual pieces don't. Emergent behavior, latency accumulation, cascading failure, coordination overhead, organizational friction. You can write perfect code inside a badly structured system and still experience constant pain. Engineers understand that structure determines friction. If teams constantly step on each other's toes, that's architectural. If small changes require touching 5 services, that's structural. If deployments are stressful, that's systemic. Programming improves local quality. Engineering improves global coherence. 3. Programmers optimize for today. Engineers optimize for time. Programming is immediate. Engineering is longitudinal. A programmer might ask, how do I get this working before Friday? An engineer asks, what will this look like in 6 months? Time changes everything. Teams grow, requirements evolve, traffic increases, regulations shift, integrations multiply. Engineering is the discipline of managing change. Every decision you make today shapes how painful change will be tomorrow. For example, hard coding values may be fine now, but if those values change frequently, you've created future friction. Skipping tests might help you ship today, but it increases the cost of every future change. Engineering means thinking in cost of change. Will this design make future features easier, make refactoring safer, allow independent deployment, reduce cognitive load, or will it increase coupling, hide assumptions, spread business logic across layers, create fragile dependencies? Sometimes the correct engineering decision is to accept short-term debt. But engineers make that trade-off consciously. Programmers often make it unknowingly. 4. Programmers work alone. Engineers coordinate. Even if you sit alone at your desk, you are never alone in software. Your code interacts with teammates, CI pipelines, infrastructure, product managers, QA, customers, future maintainers. Programming can be solitary. Engineering is collaborative. A programmer might think, this works on my machine. An engineer asks, does this work in staging? Does this work in production? Does this fit into the deployment process? Does everyone understand how to use this? Engineering requires shared understanding. That means writing documentation, leaving clear commit messages, explaining trade-offs in pull requests, recording architectural decisions, participating in design discussions. If knowledge only lives in your head, you've created a risk. If only one person understands a system, that system is fragile. Engineering maturity includes communication discipline, because alignment scales better than heroics. 5. Programmers avoid constraints. Engineers design them. Early in your career, constraints feel frustrating. Why can't I just import this library? Why can't I access the database directly? Why do we need this architecture layer? Why do we have strict code review rules? It can feel like bureaucracy. But engineers understand something subtle. Constraints reduce chaos. Boundaries prevent accidental coupling. Code review prevents silent decay. Layered architecture prevents dependency sprawl. Without constraints, everything depends on everything. Data ownership becomes unclear. Responsibility blurs. Changes ripple unpredictably. Constraints create clarity. For example, if you need user data, go through this service. That's a restriction, but it ensures consistency, validation, and auditing. Good engineering cultures deliberately create dependency rules, API contracts, style guides, versioning policies, review processes, not to slow development, but to preserve long-term flexibility. Freedom without structure leads to entropy. Engineering is structured freedom. 6. Programmers measure output. Engineers measure outcomes. Programmers often measure productivity in visible artifacts, lines of code, features delivered, tickets closed, story points completed. Engineers measure different things: user adoption, system uptime, lead time for changes, deployment frequency, change failure rate, mean time to recovery. Because writing more code does not automatically create more value. Sometimes deleting code creates more value. Sometimes simplifying a workflow has more impact than adding a feature. Engineers care about leverage. If improving CI reduces deployment time by 50%, that may unlock faster iteration, reduce stress, fewer errors, higher morale. But that work may not produce visible features. Engineering maturity means focusing on impact, not activity. Output is what you produce. Outcome is what changes. And engineering is about changing reality in meaningful ways. 7. Programmers see errors. Engineers see risk. A programmer sees a bug and fixes it. An engineer asks, why did this bug happen? Is it a missing test, a process failure, a monitoring gap, a design flaw, a communication breakdown? Engineers look for patterns. If deployment failed once, what does that reveal about the pipeline? If a race condition appeared, what does that reveal about concurrency assumptions? If a misconfiguration caused downtime, what does that reveal about environment management? Engineering is proactive risk reduction. It's about building systems that fail predictably, fail visibly, fail safely. Engineers implement automated tests, monitoring, alerts, postmortems, runbooks, not because failure is likely, but because failure is inevitable. The question is not, will something go wrong? The question is, when it does, how contained will it be? Programming reacts to errors. Engineering designs for resilience. 8. Programmers think in files. Engineers think in flows. Programmers often navigate by file. Open file, edit function, fix bug, save. Engineers trace flows. User request to API gateway to service to database to cache to external dependency, deployment to CI to artifact storage to container registry to runtime, feature idea to specification to design review to implementation to testing to release to monitoring. They think in end-to-end journeys. When a user clicks a button, an engineer asks, what happens next? Where does the request travel? What systems does it touch? What happens if one of them is slow? What logs are generated? Where are metrics recorded? What's the rollback plan? This system's perspective reveals hidden complexity. A change in one place might increase database load, trigger new caching behavior, affect background jobs, introduce race conditions, break reporting pipelines. Thinking in flows means you don't just see code. You see motion, you see dependencies, you see consequences. And once you start thinking this way, you stop being surprised by unexpected behavior, because you've already mapped the system in your head. The real shift. The shift from programmer to engineer is not about seniority, it's about perspective. You can be a junior engineer with an engineering mindset, and you can be a senior programmer stuck in implementation mode. The difference is this. Programmers ask, how do I build this? Engineers ask, should we build this? Where should it live? What will it cost later? Who owns it? What happens under stress? Engineering thinking reduces surprises. It reduces rework. It reduces fragility. It increases long-term velocity, and it makes you exponentially more valuable because companies don't struggle with writing code. They struggle with managing complexity. How to start thinking like an engineer. If you're early in your journey, here are practical shifts you can make. Before coding, write down the problem in one sentence. Define success criteria. Identify dependencies explicitly. Ask what could fail. Think about how you would test it. Consider how it might need to change. Document architectural decisions, even in small projects. Review your own code as if someone else wrote it. Ask for feedback constantly. Read post-mortems from real-world system failures. These habits compound. Over time, you'll notice something interesting. You start preventing problems before they appear. That's engineering. Final thoughts. Stop being just a programmer. Programming is necessary, but it's not sufficient. Start being an engineer. Think in systems. Think in time. Think in trade-offs. Think in ownership. Think in risk. Think in outcomes. That's the difference between writing code that works and building systems that survive. If this video helped you see software differently, click like. It genuinely helps the channel. If you want more deep dives on system design, architecture, real-world case studies, and how strong engineering teams operate, subscribe to The Shape of Software. And if you want a structured next step after this, I've linked a beginner-friendly software engineering learning path on Coursera in the description. It walks through programming foundations, workflows, and how real projects actually run, without having to guess what to learn next. Now I'm curious. At what point did you realize coding wasn't enough? Leave a comment below. Thanks for watching.